Okay. Okay. All right. So let's go back to where we left off last time. So I hope you had a chance to look at some of the examples that I posted also for you. So what we talked to the last two lectures about some example problem formulations. Just very quickly, I uploaded this example and I just wanted to go through it. Sorry, I didn't share my screen. Hold on. Share the screen. Okay. All right, I hope everyone can see this now. So this was the example that we just quickly read through last time, but now let's see. I don't know if any of you tried to actually solve it. So the idea was to try to just get a feel again for solving an LP problem. We had a cargo plane that has 3 compartments for storing cargo: front, center, and rear. And there are weight capacities and space capacities for each of these parts of the plane given in this table here. Furthermore, the weight in each of these respective compartments must be the same portion of that compartment's weight capacity. So we need to maintain the balance of the plane. Then we have 4 different types of cargoes which are available for shipment, C1 through C4. And in this table here, we're given the weights in tons that are available, the volume in terms of cubic meters per ton, and the profit in terms of pounds per ton that we can make for each of these cargoes. We can accept any portion of these cargoes. So this is not an integer program. This is a linear program with continuous variables. And the objective is to determine how much of each cargo should be accepted and how to distribute them in the compartment. So we need to know how much of each cargo to put in the front, in the center, and in the rear of the plane. Okay, in terms of assumptions, we said last time, each cargo can be split into whatever portions or fractions we desire. So we're not looking for an integer solution. Each cargo can be split between 2 or more compartments. So we can have a little bit of cargo 1 in the front, a little bit in the center, a little bit in the rear, and so on. And the cargo can be packed into each compartment. So we're not looking at this in terms of this. If it was a spherical capacity, we would not be able to pack all the way to the volume capacity. We assume that we can pack all the way to the volume capacity. Okay, and what I mentioned last time, let's look now at the solution. We need to decide which variables. So the first thing always when we talk about formulating a linear program is we need to define all the decision variables. We need to formulate the objective function and formulate the constraints. In terms of variables, or decision variables, we can define them as xij to be the number of tons of cargo I that is put into compartment J. So for example, x12 would be the amount of cargo 1 in the center of the plane. X11 will be the amount of cargo 1 in the front. X13 will be the amount of cargo 1 in the rear, and so on. Okay, now the question is, let's start with trying to formulate these constraints. So first of all, we cannot pack more of each of the 4 than each of the 4 cargoes that we have available. So that's our first set of constraints, and that's this here. So the x11 plus x12 plus x13, so that's the amount of cargo 1 in the front, center, and rear of the plane, has to be less than or equal to the 18, which is the amount of tons that we have available of cargo 1. Same thing for cargo 2, 3, and 4. Okay, that's clear, I assume? You guys just feel free to jump in and stop me if there's something that's not clear. Okay, so that's our first set of constraints. The second set of constraints, we said that the weight capacity of each compartment must be respected. So we have to make sure that we don't overdo it with the weight. We said that we can fit, I'll scroll back a little bit, here 10 tons in the front, 16 tons in the center, and 8 tons in the rear. So when we look at the amount of cargo 1 in the first compartment, plus the amount of cargo 2 in the first compartment, 3 and 4, their sum in terms of tons has to be less than or equal to 10. Same with the center and same with the rear of the plane. So this is the weight capacity constraints. Okay, what else? Any ideas? Anyone? Feel free to unmute. I'm not looking at the chat, so okay. I'll keep going. You guys unmute if anyone has an idea. We said that the volume capacity of each compartment must be respected. So we said how much each ton of each of the cargoes takes in terms of cubic meters per ton. So again, we summarize across all of the cargo that is in compartment 1, and that has to be less than or equal to the volume or the space capacity of the front of the plane. Same with the center, same with the rear. Okay, so these are our volume capacity constraints. And finally, we said that the weight of the cargo in the respective compartments must be the same proportion of that compartment's weight capacity. So if we know that the weight capacities are 10, 16, and 8, which was given in the initial table, then the same, we have to maintain that same proportion. So when we summarize all of the tons in the first compartment divided by 10, that has to be equal to the sum of all of the tons in the second compartment divided by 16, and the sum of the cargo in the rear divided by 8. So these proportions we have to maintain them because of the balance of the plane. Okay, what is our objective function finally? So that was our constraints. How would we formulate now the objective function? Any ideas? We said we want to try to maximize our profit, right? I'll scroll back up here a little. So how would we formulate the objective function? Any ideas? No, no one is jumping in today. Okay. All right. So the objective is to maximize total profit. Okay, we said our profit is 310 pounds per ton for cargo 1. So we summarize all of cargo 1, which is in the front, center, and rear of the plane, plus 380 is our profit for cargo 2. We summarize all of the different tons of cargo 2 distributed through the plane. Same with cargo 3, same with cargo 4. Okay, so that would be, this is our formulation. So we have this objective and we have the different constraints. So if you're ever given a problem like this, it's important to read carefully through the problem, and like I said, maybe in the initial lecture, maybe even in words, write down all of the constraints first. So make sure you understand them before even trying to formulate them, so that you don't forget something. Okay, and that's about it. Also, we know that all of the variables x11 through xij, so all of the variables have to be greater than or equal to 0, right? I don't think that's stated here, but we would need to add that as well. Okay, it is over here, up here. Okay, any questions about this example before I go on? All right. Okay. So again, this was just to give you an idea of how to formulate these different types of problems. I also gave you an example branch and bound question, which is similar to what we had in the lecture, just so you can try it. So we have the. By the way, did you guys see this? So I uploaded this to Fair Web. I don't think I put these examples on Teams, but I can add them there as well. Did you guys see these files? Someone? Yes or no?
You uploaded them.
Okay, just to make sure that they're visible too. Okay, so this is an example branch and bound. We have the following mathematical problem. We're trying to minimize this equation. Try on our variables are x1, x2, x3. So we're looking for the values of x1, x2, x3, which minimize this expression, subject to a number of constraints. We also know that x1 and x2 are integer variables, and x3 is a binary variable. We solve the LP relaxation of this problem. Again, what do we mean by solving the LP relaxation of this problem? Anyone?
We ignore that the numbers x1 to xn are integers, so we assume they are just ordinary real numbers, and we solve a linear programming problem.
Okay, how would we formulate the LP relaxation concretely of this problem? So we know that, so we can, what do we do in terms of this formulation here? How do we modify it so that corresponds to the LP relaxation?
We delete the last 2 rows.
Okay, the last 2 rows. So we just have this. But would it make sense, since we know that x3 is binary, to also add one more thing? Any ideas? So we can just delete these 2 rows, but we can also add one more thing. So if we say that x3 is less than or equal to 1, sorry, why do I have it here? So this should be 1. Hold on. Okay, so we know it's binary. This is still an LP relaxation, so we removed all integer constraints, but we know that x1, x2, x3 are greater than or equal to 0. We removed the fact that they're integer variables, so we relax that constraint. But since we know that x3 is binary, it can only be 0 or 1. We can also add this constraint that x3 is less than or equal to 1. Okay. Okay, is that clear? All right, so this is our, if we say formulate the LP relaxation of the problem, we have the same objective function. The constraints are the same, except the fact that we now relaxed this integer constraint, right? And we have this binary variable, so we also say that that's greater than or equal to 0, less than or equal to 1. Okay, what does the LP relaxation solution provide? We all went through this last time also. Is it an upper bound, a lower bound, or an optimal solution to the integer linear program? In this case. In this concrete case. Okay, guys, someone, I'm sure you all know this. So if I solve the LP relaxation, I remove the integer constraint, so I'm allowing any solution possible. Is that going to give me an upper bound, a lower bound, or an optimal solution to the integer linear program?
Lower bound.
Okay, so it's going to give me a lower bound. I know that there's no way I can find a better solution than that. Since it's a minimization problem, then we're talking about a lower bound. It would be an optimal solution if the LP relaxation gave me variables, an integer solution, and also x3 is binary. In that case, then my LP relaxation, and only in that case, would it be the optimal solution to the ILP. Okay, the figure below illustrates the steps of a branch and bound algorithm. If we choose a variable, right, corresponding value, 2 new subproblems for nodes 2 and 3, and list the fathoming tests. So we went through these tests last time, which we used to conquer these nodes or subproblems to tell us whether we keep searching or whether we've conquered a certain node and it doesn't make sense to go any further. So if we take x1 to be z star here, 1, 1, 1, it gives us we have an integer solution. It gives us a value of 10. Now the question is, can we find a better solution? If we solve the LP relaxation to the initial problem, we get a solution of 5.11, and these are our variables, 5 ninths, 1 ninth, and 1. Now we said that we take x1 to be the branching variable, so x1 is less than or equal to 0 or greater than or equal to 1. We look at the first. Then we actually formulate now the 2 subproblems. When we say we need to formulate the 2 subproblems, what I want to just point out here is that these are now not LP relaxations, but now this is the original problem with all of the constraints that we had originally. Just we added this last constraint that x1 is less than or equal to 0 or greater than or equal to 1. Okay, so the subproblem is not an LP relaxation, but it is the original problem, just now with this added constraint here that we use to branch. Okay, once we've split up, so subproblem 2 is going to have the same, is going to be the same as subproblem 1, just the only difference is going to be this last constraint related to x1. Now what do? Now we go through these fathoming tests. We look at let's look at subproblem 1. We look at, does the LP relaxation have a solution, first of all? And so we solve the LP relaxation of subproblem 1, and we find that there is no feasible solution in that case, which means that if there is no feasible solution to the LP relaxation, then there is no feasible solution to the integer problem, right? Does that make sense to everyone? Is someone that is not clear on why that is? Okay, so as soon as we found that the LP relaxation has no solution, that means we have conquered this this node. We don't need to go any further. If we look at node 3, let's look at, does the LP relaxation have a solution? Yes, it does. So we find that it has a solution, and it's shown over here. The LP relaxation to node 3 is 7, and with variables with values of x1, x2, x3, x3 is 1, 0, and 1. Is the lower bound greater than or equal to the solution the best solution we have so far? Because if it is, then there's no need to further, we're trying to find a better solution than the one we have. If the lower bound is already greater than what we have, then there's no way we're going to find, and there's no better solution in that sub-branch. So we don't need to keep looking. But in this case, that's not true. And finally, the third test, so we should keep going. And if we look at the third test, is the optimal solution to the LP relaxation integer? Yes, it is. Therefore, we have found an integer solution. This is the best solution possible in this from this node onwards. Therefore, there's no need to keep going. Okay, so we found the optimal integer solution. Okay, is that clear? Any questions? All right. Okay, so I just wanted to go through these examples because some examples like this might come up on the midterm. So just to make sure everyone's clear. Okay. So let me now go back to the dynamic programming, just a few slides that we had left from last time, but I'm going to stop recording now and start again so that we have split up the videos.